Start.
Good morning, everyone. I am Pratham Kembulkar, and along with my teammates Darshan Rai Gandhi and Raj Shinde, I will be presenting our work titled Characterizing Quantum Tunneling Effects, or GIDL, across CMOS technology nodes. This project explores how gate-induced drain leakage behaves as transistors are scaled down from 180 nanometers to 45 nanometers. The scaling challenge. For several decades, Moore's law has guided the miniaturization of transistors, allowing us to pack more devices onto a single chip and achieve faster, more efficient circuits. However, as transistors become smaller, leakage currents, currents that flow even when the device is supposed to be off, have emerged as a major design challenge. Earlier, dynamic power dominated total power consumption, but in today's nanoscale devices, static or leakage power has become comparable or even higher. There are multiple leakage mechanisms such as subthreshold leakage, gate tunneling, and GIDL or gate-induced drain leakage, which is the focus of our study. GIDL or gate-induced drain leakage occurs when a transistor is in the off state but still allows current to flow between the drain and substrate due to band-to-band tunneling. This tunneling happens in the high electric field region near the gate-drain overlap, where electrons tunnel from the valence band of the substrate to the conduction band of the drain. The GIDL current depends exponentially on the electric field and therefore is heavily influenced by oxide thickness and the gate-to-drain voltage. As technology scales down and oxides become thinner, these electric fields intensify, making GIDL an increasingly critical issue in modern CMOS devices. Accurately modeling GIDL is essential for predicting device leakage and ensuring circuit reliability. If GIDL is underestimated, low-power designs may fail to meet their leakage or noise specification. In analog and mixed signal circuits, GIDL can alter bias conditions and distort signal linearity. This is why a precise understanding and modeling of GIDL across technology nodes are necessary for both device engineers and circuit designers. Now, my teammate Darshan will take over.
Okay, so I will be explaining the methodology. To analyze the GIDL accurately, we developed a hybrid Verilog, a modeling framework. We began with standard GPDK transistor models available in the Cadence Virtuoso, which represents typical CMOS devices at 180 nanometer, 90 nanometer, and 45 nanometer. However, these models do not fully capture the physics of tunneling leakage. So we built a custom Verilog, a module that mathematically describes the band-to-band tunneling current using physical equations. We then place this module in parallel with the standard GPDK transistor in a Spectre simulation environment. The GPDK model simulated normal device behavior while our Verilog, a model injected in the missing GIDL current, allowing a realistic physics-based representation of leakage process. The problem with the GPDK model is when we compared simulation results across different nodes, we discover a major issue. The 180 nanometer and 90 nanometer GPDK models fail to reproduce GIDL at all, as shown in the figure. They showed only linear increase in leakage current, which corresponds to ohmic behavior not to be expected exponentially in band-to-band tunneling behavior. Only the 45 nanometer model displayed a realistic exponential GIDL curve. This finding indicates that directly comparing leakage across nodes using unmodified GPDK model is misleading. Hence, our hybrid model framework was crucial to obtain meaningful and comparable results. The few of the results are shown on the next slide. For GPDK 45 nanometer technology. Using our hybrid framework, we were able to extract accurate GIDL behavior at 45 nanometer technology node. We found that GIDL current scales linearly with transistor width because a wider channel provides larger tunneling area. It also increases significantly as channel length decreases due to short channel effect that enhance the local electric field. The table shown shows all the values and all the analysis. Overall, the GIDL current grows exponentially with scaling, confirming that quantum tunneling becomes increasingly dominant at advanced nodes. Our result highlights that even small changes in device geometry or bias can lead to large variations in leakage current. From now on, my teammate Raj Shinde will take over.
So, okay, we'll now come to PMOS and mixed signal impact. We have also examined PMOS devices and observed that even at 45 nanometer, the standard GPDK PMOS model oversimplifies the GIDL effect, showing a decreasing rather than increasing leakage with voltage. This suggests that model fidelity remains a limitation even at modern nodes. From a circuit perspective, GIDL has a direct impact on mixed signal systems such as digital to analog converters. In DAC switches, GIDL causes port-dependent leakage, which degrades accuracy by increasing differential nonlinearity and integral nonlinearity. Therefore, understanding and mitigating GIDL is essential not just for transistors, but for maintaining the linearity and precision of entire circuits. To conclude, we successfully characterized GIDL across 180 nanometer, 90 nanometer, and 45 nanometer nodes and identified critical limitations in standard GPDK transistor models. We have also developed a novel hybrid Verilog, a framework that accurately captures GIDL physics, enabling realistic modeling of tunneling leakage. Our analysis confirms that GIDL increases exponentially with scaling and strongly depends on both devices, geometry, and bias conditions. Finally, we demonstrated that GIDL has a tangible impact on mixed signal circuit linearity, emphasizing the need for validated device models in low power designs. Acknowledgement. We would like to thank the Department of Electronics and Telecommunication Engineering, Vidyalankar Institute of Technology, Mumbai, for their guidance and resource throughout this project. All simulation data and Verilog code are available on our GitHub repository. Thank you for your attention.